Welcome for the second lecture on artificial intelligence in robotics. And this lecture is about robotics paradigms and control architectures. And in some perspective, this lecture can be seen as an overview, and maybe for some of you, maybe a bit tedious, but from my experience, these paradigms and maybe a little bit look up to the history should provide you the background that almost all of the ideas you will have during solution of some robotic system, they already have been raised and have been proposed some solutions, and this is something that you can build on, and maybe you can return to this lecture after some experience on the robotic systems, because what is quite important that any autonomous, especially autonomous robotic system, is a very complex, and you need to follow some guidelines and ideas how to organize the things and how to create a system that is reliable, robust, and that is behave as you like. So let's start with the paradigms. And we will follow what has been taught on the first lecture, what is the robot. And the robot has some sensors, has some control and also actuators. And related to this, and what you can see in the video is a robot that uses its sensors to actually create a model of the environment and then use this model to plan its action and then execute these actions. So this is in a very sense using the primitives of robotics. This is the sense, plan, and act. And the combination of these primitives form a control architecture. It is also called robotic paradigm. We can find three architectures or paradigms combining sense, plan, and act primitives. The first is the very intuitive and probably the most AI and approach, which is the hierarchical paradigm, and it is purely deliberative system. So we assume that we sense the environment, we plan in the model of the environment, and then we act. And there are some drawbacks of this. We will cover it in a few moments. And as a response to the drawbacks of the deliberative architecture, there was the reactive paradigm. That's actually the computational bottleneck in planning is removed, and we have reactive control. And of course, it also has some drawbacks. So the combination of these two hierarchical and reactive paradigms in hybrid paradigm combines the benefits of both architectures. So let's start with the hierarchical paradigm. So the robot senses the environment and creates the world model. The world model can also be a priori available, for example, as a previously built or sketch a map. Then the robot use this model to plan its action, and then it's executed. Of course, that the advantage of this is in clear ordering between the primitives. And the very first robot, AI robot, Shaky, actually follows this deliberative architecture, and also steer a bit the research in the autonomous systems and robots. So in the deliberative architecture, we need some algorithms for planning. We look forward for generalized algorithm, and such relatively very general problem solver is Strips, and you will be, or you already are familiar with that from other AI courses. But the important part of this hierarchical architecture is that we assume the closed world. So the robot is able to model or reason about everything that it is needed, which is for some isolated deployments, eventually possible, but we will see what are the drawbacks. So, as you can imagine, having a very detailed model of the world, it is computationally demanding. And the planning can be very slow using the global world representation that also contain all possible information needed for planning. And what is quite important that using this planning that is computationally demanding, that takes some time, the sensing and acting is always disconnected. Because that takes some time to reason about the world, reason about the possible action, but the world can change. So the global world representation has to be up to date. And we need to update it frequently to achieve a sufficient accuracy of the particular task. So if there is a demand on speeding up or improving performance of planning algorithms, it's because we need to have this close, fast loop of sensing, planning, acting. And general problem solver, you probably also touch this in domain-independent solver, are very powerful, but it also needs many facts about the world to search for a solution, and maybe facts that are not relevant. So searching for a solution in a huge search space is quickly computationally intractable, and the problem is related to the so-called frame problem, which means that even a simple action needs to reason over all irrelevant details. So the frame problem is a problem of representing the world situations to be computationally tractable. So we like to decompose the world model into parts that best fit to particular type of action. And some of the examples of existing hierarchical models where you can take the information and background, because that has already been deployed, and you can see what are the properties. And one of them is nested hierarchical control and an SIT real-time control system. And it has been used for a while to 80s when the focus has been changed to reactive paradigms. And we will talk about the reactive in a few moments. So the development of hierarchical models exhibit additional advancements, such as a potential to address the frame problem. And also provide the way how to organize building blocks for control architecture. And this is quite related to actually software development, because in addition to the hardware part, the intelligence is in the software, and you need a way how to organize your software that will exhibit the desired behavior of the robot. So, and very important part, which is having the computational power we have today, is becoming more and more relevant, is that the hierarchical model represents an architecture that supports evolution and learning systems towards full autonomous control. So once you will set up the system and you deploy it, you like to make a self-improving system, which is, for example, one of our research stream in my lab. So anyway, what is the nested hierarchical controller? So, and this is a possible schema that you can use in designing your system. Maybe some of the blocks, you will call them a little bit differently nowadays, but the principle or the main idea is the same. So we have the sense, plan, act. We have this loop, so we are acting to the environment that is sensed through the sensors. We create a world model. We have the mission planner, that is, for example, a decision where the robot should go, and a navigator or navigation, which is responsible to design how to reach the goal, to find a path that avoids obstacles and so on. And there is a pilot, there is a controller that for example can be the trajectory follower or path follower that actually communicate with low-level controller that drive or steer the actuators. And here we have something which is a bit faster loop, right? That if you control some robotic arm and you have this position controller, and you may eventually quickly send some obstacle and steer the control. So what are the NSIT real-time control system properties? It's quite interesting that it's motivated to create a guide for manufacturers for adding intelligence to their robots. So it is based on the nested hierarchical control architecture, and the main feature it introduced is a set of models for sensory perception. It introduced pre-processing step between the sensor perception and the award model. Of course, that from nowadays perspective, it's obvious, but in these or that times it was something new. So, and what is the sensor pre-processing is called feature extraction. So you can imagine that you have a camera, you capture the image, but you will not use the whole image pixel per pixel, but you will extract some features, important features that are relevant to your problem, such as a salient object that can be used for localization for a while because they are persistent in a short period. And it also introduced a very interesting concept, which at the time was called value judgment module. And it is the idea that once you create a plan, you use a simulation of the plan to ensure it's feasible. Because creating a feasible plan is important, and doing that in the planning means that you need to include all possible constraints. So you can a little bit simplify the planning, and then you can ensure feasibility. And then the plan is passed to behavior generation. That is module to convert the plans into action that are performed. That is the act. And of course, this behavior is utilized in reactive and then in hybrid architectures. So let's take a look to the real-time control system. So we have the sensor perception, and we create the model. We have some database, and here we have this value judgment. These are the simulated plans, and we have the behavior generator. So we plan, we have the task and goals, and then we have the commanding action. The reactive paradigm. The reactive remove the planning, which was the bottleneck, and we have a sense act. So it's also biologically inspired, as humans and many animals provide evidence of intelligent behavior in an open world. So our world is very complex. So it might be possible to overcome the closed world assumption. And even that we take a look to insects, fish, or other simple animals that exhibit intelligent behavior, but has virtually no brain, so there is no these computational resources. So there must be a mechanism that that avoid the frame problem. So, and this, since it's biologically inspired, we need some terms to describe properties of intelligence of various entities. And I actually like the computational level theories by Tomar. And let's think and talk about it a bit. So agent is a self-contained and independent entity. Okay, it can interact with the world to make changes and sense the world. It has self-awareness, and from the computational point of view or intelligence point of view, we can consider a computational level, what and why. What is the goal of the computation and why it is relevant. So still consider that we are addressing the frame problem to be focused on the important part for the relevant decision. So algorithm level is then answering to the question how. So it's focused on process rather than implementation. So how to implement the computational theory? What is the representation of input and output? What is the algorithm for the transformation of the input to the output? And then we have the physical level, and that's the question: how to implement the process, how to physically realize the representation and algorithm. So related to the reactive program, important part is behavior. We can consider a behavior as a mapping of sensory input to a motor action, a pattern of motor action. So if we send something, we do that something. And again, you can take a look to the biology, and behaviors can be divided into three categories. The reflexive behaviors are, let's say, hardwired. There is stimulus response. So once is there stimulus, it is directly connected to the response. This is the fastest response time. There are reactive behaviors learned, and they are then executed without conscious through. So you can consider that behaviors based on muscle memory, such as biking, skiing, or are reactive behaviors. So once you train yourself to bike or to swim, and you are not thinking about how you will coordinate your legs and arms. So it is reactive behavior, and you use the muscle memory. Let's say. There are conscious behaviors that are deliberative as a sequence of the previously developed behaviors. So in ethology, reactive behavior is learned behavior, while in robotics, it connotes a reflexive behavior. So that's because you as a robot designer, you are hardwiring reflexive behaviors. So take a look to the fast hardware reflexive behavior. If there is a sense, they produce the action, and we can further categorize into three types. There are reflexes. The response lasts only as long as the stimulus. So the response is proportional to the intensity of stimulus. And there is taxis. That response to stimulus results in a movement towards or away of the stimulus. So if an insect is attracted by light, that started and move towards light, and there can be also fixed action patterns. So the response continues for a longer duration than the stimulus. So even that the stimulus is appear, then still the action is performing. And of course, these categories are not mutually exclusive, because you can consider some combination, and an animal may keep its orientation to the last sense location of the food source, that is taxis, even though it loses the sight of it. So it's a fixed action pattern. But this notion should provide you some background and motivate you to reason about, okay, there are differences, and now if you are experienced in programming, you can think, okay, I will do that in that way regarding the particle implementation. So how behaviors can be acquired? Again, from ethology provides some insights into how animals may acquire or organize the behaviors, because one of them is innate. So the insect or animal is born with a behavior, it is pre-programmed, and there can be a sequence of innate behaviors. Be born with the sequence. So the sequence is logical but important. So, and each step is triggered by a combination of internal state and the environment. So because you are a computer scientist, you are experienced with the finite state machine, so you can immediately think, okay, I will realize that using some finite state machine. And the other type is the innate with memory. So be born with behaviors that need initialization. And this is quite interesting example of the bees. So a bee doesn't appear with the null location of the hive. So it has to perform some initialization steps to learn how the hive looks like. So it performs some like initial flights and actually learn how to recognize the hive. And the stimulus response types of behaviors are simple to pre-program, but it certainly should not exclude usage of memory. So this is something that maybe you can be confused. So reactive doesn't mean that you are not using the memory, right? That's all. And of course, that some behaviors can be learned. You can learn a set of behaviors. So, and what is important, if there is a behavior, you also need some releasing mechanism and to stop or suppress the behavior. So it can be based on the internal state and or motivation that can release the behavior. So once being hungry results that you are looking for a food. So behaviors can be sequenced into complex behavior, and innate releasing mechanism is a way to specify when a behavior gets turned on and off. So the release acts as a control signal to active a behavior. And if the behavior is not released, it doesn't respond to sensory input, so it's suppressed. And it doesn't produce the motor outputs. So you can imagine that in our block schema, we have the sensor, we have the behavior that defines what will be the motor action depending on the sensor. But we are waiting for the release of it. Or once the behavior is suppressed, it's not acting. And of course, the releases can be compound and multiple conditions have to be satisfied to release the behavior. And now we may start struggling how to organize the behaviors. Because the behaviors can be concurrent, of course, and can be executed independently, which may have different results depending on the interaction. So we can, for example, identify equilibrium, that the behavior seems to balance each other out. So undecided behavior or squirrel, whether to go for food or rather run, avoiding human. So if you are in a city park, especially in the US, for example, then you may experience that there are these squirrels and they are going for the food, for some trash bins, and once they see the human, they are avoiding, but because they are hungry, so they go again. So they are moving there and back. Or there could be a dominance of one, so winner takes all, as only one behavior can execute and not both simultaneously. Or there can be a cancellation, so the behaviors cancel each other out. So one behavior going to light and the second behavior going out of light, so there can be some I will not say it's not the equilibrium, so it will nothing happen. So simultaneously motors are going right and simultaneously the command is sending motors left, so motors will not move. And it is not known how different mechanisms for conflicting behaviors are employed in animals. But it's important to be aware how the behaviors will interact in a robotic system. So let's summarize the behaviors. So behavior is a fundamental element in biological intelligence, and it's also a fundamental component of intelligence in robotic systems. Complex action can be decomposed into independent behaviors, which couple sensing and acting. The behaviors are inherently parallel and distributed in comparison to the deliberative system. A straightforward activation mechanism, like a Boolean variable in our computer program, may be used to simplify the control and coordination of behaviors. There can be multiple perception filters used to sense what is relevant to the behavior. That's action-oriented perception. And direct perception reduces the computational complexity of sensing. So because we focus on what is necessary. It also allows actions without memory or inference or interpretation. Behaviors are independent, but the output of from one behavior can be combined with output of another behavior, and it may also be used to actually inhibit another behavior. So let's continue with the reactive paradigm that's was initiated or originates from dissatisfaction with the deliberative sense plan act, the hierarchical paradigm. And it is very much influenced by the ethology, because that can be inspired from nature. And what we can imagine is these sensors and acting, but these behaviors can be like avoid collisions, wander, explore, build a map. And we can build a map during the wandering and exploration. when the robot is moving towards a possible collision, it avoids it. So it can be run in parallel. And what is different from the sense plan act, the reactive paradigm actually exhibits horizontal decomposition. Let's a little bit summarize the reactive paradigm. So it is motivated by the drawbacks of the hierarchical, the deliberative sense plan act, and it is mostly influenced by ethology because we can be inspired from nature. And you can imagine that so we have these sensors, we have the actuators, and we can have like these four behaviors that can actually perform simultaneously. So once the robot is wandering around the environment, we can build a map, so rely on localization and mapping. If there is a movement of the robot and there is detecting a possible collision, the robot can avoid the collision also during the wandering. And we can have the simultaneously running, for example, exploration that at some point we steer the robot to actually explore some parts. And contrary to the sense plan act, which is a horizontal decomposition, the reactive paradigm, the sense act, provides a vertical decomposition. And the behaviors can be layered, and what is relatively very intuitive is that these lower layers are the survival behaviors. So we can also in this vertical decomposition, you can have some intuitive notion that okay, this is to avoid damage of the robot, damage of the object in the environment. But maybe building a map is not that important as avoiding the collisions. And of course, the upper layers may reuse the lower layers, and or can inhibit them or create parallel tracks of more advanced behaviors. And quite important regarding the reliability and robustness of the system is that if some upper layers fail, you can consider that the lower layers will still operate because that are responsible for the functionality, let's say, of the robotic system. So how to actually organize the multiple concurrent behaviors? So strictly speaking, one behavior doesn't know what another behavior is doing or perceiving, so they are completely independent. And mechanisms for handling simultaneously active multiple behaviors are therefore needed for complex reactive architectures because you like to have predefined behavior, at least if you consider that you would eventually like to have a certification of your fully autonomous robotic system that behaves as desired. So you need to control it. And there are two main representative approaches that have been proposed in the literature. And first is the subsumption architecture proposed by Rodney Brooks, one of the co-founders of the iRobot. And the other is potential fields methodology that has been studied by Ronald Arkin and David Payton and others. So take a look to some characteristics of the reactive behaviors. So robots are situated agents operating in an ecological niche. So that is some particular part of the environment. Robot has its intentions and goals. It changes the world by its action, and what is sensed influences its goals. Behaviors serve as a building blocks for robotic action, and the overall behavior of the robot is emergent because we have parallel running behaviors. And only local behavior-specific sensing is permitted. So usage of explicit abstract representation is avoided. So it's not the egocentric representation. The robot-centric coordinates of an obstacle are relative and not in the world coordinates. That's the point of view of the egocentric representation. Reactive-based systems follow a good software design principle. So I already mentioned that we need to develop the system, and we have a couple of behaviors, and we need to decompose the problem, and we can follow the same methodology as for the software design. So behaviors can be tested, behaviors can be created from other primitive behaviors. Reactive based systems or behaviors are often biologically inspired. So that's under the reactive paradigm, it is acceptable to actually mimic biological intelligence. And maybe there is not a strong reasoning in some symbolic world model, but still the robot may behave in the way that we will call it intelligent. So the subsumption architecture has been deployed in many robotic architectures that combines these different layers, and without the explicit deliberative approach, which has been exhibited in Shaky because of computational demanding planning. So there was like move, think, and the robot was not very smooth, but in the end performs the tasks. So behaviors are released in a stimulus-response way. So these modules are organized into layers of competence, and modules at high level can override, subsume the output of the behaviors of the lower layer. So this is like winner take all. The winner is the higher layer here. Internal states are avoided, and good behavior design minimizes the internal states. It doesn't mean that cannot be used, but we are minimizing that because that complicate the independence of the behaviors, and also once the behavior is suspended or suppressed, the internal state doesn't help. So, and the task is accomplished by activating the appropriate layer that activates a lower layer and so on. So you can imagine that for like exploration and mapping, we need to activate the lower layers. So once the robot decides to go or to explore or to navigate a path, then the lower layer, like this collision avoidance, will be also activated. One of the drawbacks of this is that it's not easily taskable. So if you will have a desire to create a general robotic system that can perform different tasks, it will be quite demanding, and you need to reprogram the architecture for each task. So you can find the examples of subsumption architecture, for example, in the book of Robert Murphy, and this is the sense act, and the behaviors can be like this: explore, wander around objects, and avoid objects. Okay. And we already mentioned some drawbacks of deliberative architecture, some drawbacks of the reactive architecture. So, and the result is that we like to combine both of them to actually take the best from each. So the drawback of the reactive architecture is that lack of planning and reasoning about the world. So the robot cannot plan an optimal trajectory, for example, which might be important for improving performance. So hybrid architecture combines the hierarchical deliberative paradigm with the reactive paradigm. It is started in 19th, and so we have the sense act still, the reactive, and we will put the planning in the middle. So the planning covers a long time horizon, and it can use, or it is required to use, the global world model. And the reactive part, the sense act, is for real time, for quick responses. So it seems to be natural, but maybe it's also for you quite obvious. But just imagine that in very first robot, Shaky, that was the evolution, right? So okay, let's make the deliberative. Okay, it's too slow. Let's do it reactive. Okay, it doesn't allow the optimal planning, so combine them. So you can of course define what is the role of the reactive architecture in the hybrid paradigm, and I can consider that is an extension of the reactive paradigm. And the term behavior in the hybrid paradigm includes reflexive, innate, and learned behaviors. But in reactive paradigm, it connotates purely reflexive behaviors. So maybe this is just the terminology notion, but you should be aware that we have some a little bit different expectations from both of the architectures. So behaviors are also sequenced over time, and more complex emergent behaviors can occur. You need a behavior management, planning which behavior to use, and for that we need information outside the particular model. So reactive behavior works without any outside knowledge in reactive paradigms. Of course, again, you can remember the very first architecture is performance monitors. Was the judge value module, and the performance monitor evaluates if the robot is making a progress to its goal. And this is a very important component, especially for long-term deployment of the robot. So it is important that to monitor the progress, the program has to know which behavior of the robot is trying to accomplish, because it's related to what are the. So what are the components of hybrid architecture? And in this slide, I use the terminology from the textbook, even though that you will probably call or choose a different name, but the meaning is the important. So we have a sequencer that generates a set of behaviors to accomplish a task. We have resource manager that allocates resources to behaviors such as suitable sensor. And in comparison to reactive architecture, their resources are hard-coded to the particular behaviors. So on one point, it allows like focus and straightforward, so let's say, implementation, but it also means that the applicability of the particular instance of the architecture for particular task is difficult for another task. There is a cartographer which is responsible to create, stores, and maintain a map or spatial information. So this is a global world model and knowledge representation. Of course, it not necessarily be a map, but the map is fundamental, especially for mobile robots to operate. And nowadays you can imagine not only like spatial map, but also spatial temporal map, how the location will looks like in winter or in summer. And mission planner interacts with the operator, that is the request what the robot should do, and transform the commands into the robot's term. And a construction of a mission usually consists of navigation to some place where a future action is taken. So most of our cases in data collection planning and robotic information gathering is that the robot is navigated to some particular location and it takes the sample, measure or dig the rock. And performance monitoring and problem solving, that's a sort of self-awareness that the robot monitor its progress. It's also important, especially in long-term missions. So what are the existing hybrid architectures? So there are manager architectures use agents for high-level planning at the top. Then there are agents for planning refinement, reactive behaviors at the lowest level. For example, autonomous robot architecture and sensor fusion effects. State hierarchy organizes activity by scope of the time knowledge. There is three-type architecture. Model-oriented architectures that concentrate on symbolic manipulation around the global world. For example, Sophia. Task control architecture, TCA, that is layer architecture with the sequencer agent, resource manager, navigation layer, cartographer, that is path planning layer, mission planner, that is task scheduling, performance monitoring agent, that is navigation, path planning, and task scheduling, and emergent behavior filtering. So let's take a look to task architecture. So for a mission planner, so this is the instances of these terms or these parts of the hybrid architecture. So in this particular task architecture, we have task scheduling, which is based on Prodigy. There's the cartographer, which has the global world model, in the path planning, and sequencer or resource manager is navigation, and here we can consider very general formulation of partial observed Markov decision processes, and this is the deliberative layer. So because that's hybrid architecture, we can have the reactive layer, and that's obstacle avoidance. And we can have, for example, curvature velocity method here that use the sensors to define the commands for the actuators. And of course, the sensors are used to update the work model and so on. So now I will show you an example of collision avoidance that will be an instance, a particular instance, a relatively new instance of the robot control architecture. We like the traveling robots, and you probably remember from the very first lecture. And this is an example of reactive collision avoidance, and it's biologically inspired reactive architecture that combines vision sensor and a CPG. So it's biologically inspired on both parts. And in this case, everything is hardwired. So the program just goes, and once there is a head obstacle, it tries to avoid the obstacles. So this is the expected behavior. So the robot is hardwired to go forward, and if there is an obstacle, the robot avoids it. And it is an example of combining all these reactive programs and reflexes and taxes, and so on. So what is behind? So we have the CPG-based locomotion control that is parameterized to steer the robot motion to left or right. That actually perform the avoiding maneuver. And avoiding collision with obstacles and intercepting objects can be based on various techniques. And in our case, we use visual perception inspired by low giant movement detector, which is basically a neural network that detects approaching objects. You can imagine the network here. And as a result, there is this steering command. So the robot should move left or right to actually avoid that. So how it is working? Of course, that's to move left or right. It's nice to have a stereo camera, but even that, if you will have a mono camera, like in our case, you can split the image to left and right part. We have the left MGD, which basically detect the or provide the responses that there is approaching objects, and it use some edge detector and so on. So for left and right, we have individual LGMD, and we compute the difference, and from the difference we compute the action, the parameter that will steer the locomotion. That is a parameter of the CPG. Right, that's not very precise. And here is an example how it can perform. So the robot see from this is one of the camera, or a part of the camera, see what is the approaching object. And in this sense, the object is actually approaching because the robot is moving forward. So, but it will similar work even that the object will be moving. And here now the robot actually doesn't see the approaching object because it turns right. So we need to actually remember that, and in this case there is LSTM, long short-term memory for that, and of course that you need to parameterize, and you need to learn how you should avoid that, and that's actually the result captured in this paper, but that's not that important. This example is shown here to just, okay, we talk about deliberative, we talk about reactive, we talk about hybrid architecture. And this is example of reactive architecture that's biological inspired and provide one of the way how to avoid the obstacles. And if you remember the very first video, it was the robot that perceive the environment, create a map, and then put the legs to the wooden blocks to pass the passage. And in this final part dedicated to robot control, I would like to highlight that putting things together is an integration of different parts is very important and very challenging problem. And especially for you during the labs, you will build individual modules, and for the project, you need to combine them to fully working system. So, and this should be one of the possible way how you can organize the things. So let's have this control schema for a mobile robot. So we need a localization, and once we are localized and have sensing, so we can build a map. And the sensing, perception, sense the environment, we have the raw data, but for localization, we can use just the features, as I already showed you in the last lecture. So we extract the relevant information and interpret sort of features to localize, or ORB features to localize the robot. And then we can use the raw data or RGBD data to build a map. Once we have a map and a position, we can plan a path, and we have the mission command. The robot should go there. In exploration, you will create another module that will decide the robot should go there because the robot doesn't know the location there. So once you have a path, you have path execution, and you have the actuators command that you are acting. We have the motion control. And regarding this course, it's artificial intelligence. So we will focus mostly on path planning module, because having a path and executing the path is the way how the robot acts in the environment. So motion control is an important part, as once you have a plan, a path, you need to follow it. And the motion control module is responsible for path realization. And you can have a position control that aims to navigate the robot to desired location. So in the case of our, for example, hexapod robot, we already have servo motors, smart servo motor that you will send, turn the shaft to particular position. But here, for a robotic arm or even the leg, you have a position of the foot tip. Then you have a path for the individual joints to reach that foot tip. And even more, that you have a robot body, and you like to move the robot forward, which is a sequence of this swing and stance phases of the legs. So it can be quite difficult or complex. Anyway, regarding the position control, that's okay. I will just control the actuator to reach some position. If you have a path, then you can ask for the path following. So the control aims to navigate the robot along the given path. So if the robot is very far from a path, it steers the robot motion to actually reach the required path as quickly as possible, or with the minimal error. And then there is trajectory tracking, and it differs from path following, because in trajectory planning, the controller forces the robot to reach and follow a time parameterized reference path. So in a trajectory, you can imagine that you have a time prescribed that the robot should be at this location at that time. So not only be at the position. And there are two main architectures for the controller. That is the feedback controller and feed-forward controller. And feedback controller use the difference between the goalpost and the distance traveled so far as an error to control the motors. So we have these sensors, distance traveled, but you can also imagine that this distance traveled or sensors can be very complex, and you consider that the robot should reach not the actuator, not the joint or the shaft, but the robot should reach some position. Okay, so you need to localize the robot, you need the map and so on. But anyway, that's you have the difference, and you use this arrow to the control to generate the commands. And this is something that maybe you already experience, or you can experience. Although if traveling robot, if you imagine that you have wheel robot and you command the motors to actually rotate, and the robot is stuck, it rotates, your encoders will still count, so the robot may think that, okay, I am moving, but the robot is actually not moved. And the same can happen for the traveling robot. It will perform, but due to slippage, the legs will flow, just slip on the floor, and the robot can think, okay, I am moving forward, but it's actually not. So you need another way how to monitor the robot is progressing. So even that for the feedback control of individual actuators still doesn't mean that the robot is able to reach the position. In feed-forward control, there is no feedback from the real-world execution of the perform action. And instead, a model of the robot is employed in calculation of the expected effect of the perform action. So if we have, and this is what is usually performed from a little bit higher level. So when I am talking about the robot is stuck, so you prepare a trajectory of the like foot tape. You alternate the stance and swing phases. Then you send these trajectories that are followed by the local controllers. So this is the feed-forward control. So basically, it means that you can actually combine the feedback control at the, let's say, motor level. You have precise positioning of the motor shaft, and the whole movement of the leg robot is actually feed forward. And on top of that, you can actually monitor that the robot is actually moving forward on that, for example, using some exteroceptive sensors. And this is the very last slide, and in my opinion, this is very important. And I always remember that when I was young and developing robot architecture, this was something I really miss, because since you have different levels and you actually need to think how to organize the problem, and some of the loops, control loops, multiple control loops, should run on different frequencies. So this is from Introduction to Autonomous Mobile Robots. It's not any like mandatory frequencies, but should provide you the expectations. And of course, everything depends on the maximum velocity or operational speed of your robot. So if you have like small robot moving in your living room, it is completely different story than you have an autonomous car that is driving 100 or 200 kilometers per hour on a highway, or even that you have an aircraft that is running a couple of or tens of meters per second. But this provides you the expectation that path planning, because to actually follow the path or reach some location, it takes time. So it's not necessary to perform the path planning so quickly. Once you have a range-based obstacle avoidance and you are able to sense for a couple of meters or tens of meters, you don't need to do that frequently, unless there is an object that can suddenly appear, because other objects are in the environment are moving fast. So there can be the emergency stop or emergency behavior. And of course, the underlying control of your motors requires some frequency. And for example, we are using for controlling the robot, especially if we are modeling the and we are trying to capture that the robot detect the ground. There is a contact of the leg with the ground, so we need a roughly fast control loop. And hundreds of hertz are fine, kilohertz are better. So let me just summarize that in this maybe a bit talkative lecture, I provide you an excursus of the chronology of the existing robotic paradigms architectures. We start with the Sense Plan Act, which is the deliberative hierarchical paradigm. There is the drawbacks being addressed by reactive paradigm Sense Act, and of course it has its own drawbacks. So hybrid architecture is what is currently used, and one of the example of reactive biologic inspired architecture I show you a collision avoidance using LMGD and CPG, and finally I have few remarks on robot control. And so this course is mostly about AI, so we will continue on path and motion blending in the next lecture.